Hello and welcome to my channel, and in today's tutorial I am going to explain the basic implementation of AES algorithm in Python. And the reason I wanted to do this video is I am very new to Python and cryptography itself. I don't know much about them, and I'm very much open to comments that if anyone wants to point out a mistake that I have made and maybe correct it, I would be grateful for them. And that's it. And I wanted to make this video because when I was searching on the internet on how to do a basic encryption and decryption in Python using AES, there wasn't a very good tutorial on any of YouTube, Reddit's, Quora's or Stack Overflow's that explained the whole process from 0 to 100, and it was very hard for me to figure it out all by myself. So if I just skip on to the next slide, you can see that there are some key terminologies, for example CBC, ECB, padding, key, block size, hashing, and each of these terms are very crucial for the process of encryption and decryption. And in some cases those videos or tutorials used padding, they in some cases didn't use padding, in some cases they used a direct key which is in the form of bytes, but they didn't actually prompt the user for providing them a password. So that is very impractical. In a real life application, you want the user to enter a key. So many things were unexplained in those videos or tutorials. So that's why I had to figure it out by myself. So I wanted to make this video for if any new learners want to do the same like me, that is encrypt and decrypt something in Python using AES, they can know the full process from 0 to 100 with the full explanation of what's happening behind the scenes. So that's why I wanted to make this video. So let's move on to the main topic, that is, what is encryption? So the process of converting meaningful data into code which is unreadable or not meaningful to prevent unauthorized access is called encryption. So in the language of cryptography, converting a plain text to a ciphertext provided a key or a password, and decrypting that ciphertext back to the plain text using the same key is called encryption. Now there are also types of encryption such as symmetric and asymmetric encryption where the key can be different, but we are not going to that topic today. We are just going to concentrate on AES algorithm in this video purpose only, and that's what we are talking about. So AES is symmetric, which means the same key is going to be used for both encryption and decryption. So I love Python. So what is the problem that is going to be happening if we do not use encryption? So if I am sending I love Python to my friend, maybe Alice, in the form of plain text, which is I love Python, there is no problem by itself. But what if there is a hacker in the middle? So the hacker can read whatever I just sent to Alice. So what if I am sending my bank account details to Alice for some reason, and the hacker can also see the same things which Alice can? So the hacker also knows my credit card number, my bank account number, my phone number, my password. If the hacker can also see that, now he can steal money. So that's what we do not want in real life. So that's why WhatsApp, Facebook, Messenger, Telegram, they are working so hard on their encryption so that things can remain secret between two parties. So that's why we need encryption in our real lives. So in this case, we are going to use AES for encryption and decryption both, provided with a password. And what actually happens is the algorithms use something called a key, which is by default not exactly the password, but it's also the password. It's kind of complicated. So there are higher functions in later processes, like where the key is derived from a password and the key is kept secret, and many things can happen on that level of encryption, but we are not going to be discussing them. We are going to stay simple on this. So maybe the password is hello. So, and let's pretend the key also being hello. So I love Python is encrypted using AES algorithm using the password or key hello and being sent to Alice. Now, like any hacker, Alice couldn't also read the message. She needs something, that is the key. So maybe I call her up and say that I have encrypted the message using AES algorithm and the password is hello. So she can decrypt the message back to I love Python. So as you can see, encryption is a two-way mechanism, right? So anything that can be encrypted with a password can be decrypted back with the same password. Alright? Now let's move on to some key terminologies that we need to remember. For example, the modes of encryption, that is in case of AES, ECB, that is electronic code block, CBC, that is cipher blockchaining mode, and then padding, key, block size, hashing. These all terms are very crucial to the process of encryption and decryption. So padding is something that I'm going to explain just in a few minutes. Key is whatever I just told you is the password, which is hello in this case, is going to be used for the sake of this example. Block size is basically specific to the algorithm of encryption. For example, AES uses a specific block size, DES uses a specific block size, and by block size I mean that they are only used in block ciphers. So what a block cipher is? A block cipher is an algorithm that encrypts a fixed size of n bits of data at one time, which means whatever you provide to the block cipher is going to break the data into blocks of a specific length and then encrypt each of them at one time, and then at the last of the process the whole encrypted blocks are going to be appended together to get a final block of a whole encrypted text or encrypted file. So that is basically block ciphers. So block ciphers are used widely nowadays, and AES is one of the most popular standards. For example, your current Wi-Fi is probably using AES as the encryption mode. So AES is a block cipher, and I just told you the block cipher encrypts a fixed size of length of a data at a single time. So AES, for example, uses a specific block size of 16 bytes, whereas DES, if the mode was DES in this case, it would be the block size of 8 bytes. So we are not going to talk about DES today, we are only going to talk about AES. And as you know, as I just told you, AES uses a 16 byte block size, and the last one is hashing. So hashing is a very big topic by itself, so we are just going to be staying on top of what hashing is. So a hashing is basically a complex mathematical calculation to map data of an arbitrary size to a fixed length value. So what am I saying is, if you hash a whole movie which consists of 1,000,000 bytes, maybe it's going to spit out a fixed length size, and if you also take just a name, maybe Alice, and hash it out, it is also going to provide a fixed length value. So hashing is basically used in one of the applications of hashing being authentication of data. Another use might be to check if the data has any integrity. So for example, if I send you a file which has a hash value of 12345 and you receive the file, you hash it back and you say that the value is 12345, that's how we know that the file is completely okay. There was no loss of bits in time of transit. So that's how we check integrity of the data. So hashing we are going to use in this video as a stretching mechanism. For example, the key hello is not of a specific size. We need the size for a reason. I'm going to talk about it in the later slide. So we need hashing in this video to stretch out a key to spit out a fixed length size that we can use as the key that AES needs. So let's move on to the next slide. So let's talk about AES a little bit. So as I just told you about block ciphers, that a block cipher is an algorithm that encrypts a fixed size of n bits of data at one time. So does AES, because AES is a block cipher. So AES uses a fixed length block size of 16 bytes, which means everything you pass to AES is going to break the sentence or break the file into sizes, into blocks of 16 bytes and encrypt each of them at a time. In the left side of the video, I told you that the key taken is also a fixed length of 16, 24 or 32 bytes. Of course, the more the merrier. So the stronger you need the encryption to be, you use the higher. So for example, if you need the encryption to be just a simple encryption, you can use a 16-byte key. But if you want a strong encryption, you would want to use 32 bytes. But also you have to keep in mind that 32 byte will take more CPU cycles and more computer time to actually encrypt or decrypt the data. So in short, this picture says that AES uses 16, 24 or 32 bytes of fixed length key sizes as the key to encrypt the data, which is going to be broken down in fixed length block sizes of 16 bytes. So let's move on to the next slide. So if I take an example sentence, for example, I love Python more than anything in the world, is of 45 characters, right? So how will AES break them into blocks of 16 bytes? Let's check that on the next slide. So AES broke down the sentence. So the first block is 16 bytes long, and just let me say this, as these are all ASCII characters and each ASCII characters represent each byte. So even these spaces are considered 1 byte each. So the first block has 16 bytes, the second block also has 16 bytes, but the third block is only 12 bytes long, because in space D space world is basically 12 characters. So we need to make it 16 for AES to work. So how could I do that? On the next slide, if you can see that I have manually added 4 parentheses to the third block to make it a 16-byte block. So the first block has 16 characters, the second block has 16 characters, now even the third block has 16 characters. That's how AES will now work flawlessly, because all the blocks in this particular example is of the size 16. So now AES will work. Let's move on to the next slide where we discuss the operations. Okay, let's talk about the modes of encryption of AES, and there are lots of modes of encryption in AES, and we are just going to talk about 2 of them today, that is ECB and CBC. So electronic code block and Cipher block chaining mode, and each of them works in different ways, and I'm just going to talk about them now. So electronic code block. So just let's assume for now, for this slide, that each of these blocks are of 16 byte lengths. Even if they are not, just assume in your head they are, for AES to work. So what AES ECB mode does is it breaks up a message into n blocks of fixed length of 16 bytes and encrypts each of those blocks with the same key, which is going to be hello. So the problem with ECB is if there are multiple occurrences of similar pattern of texts in the plain texts, there will be a resemblance of similar patterns in the encrypted ciphertexts as well. So if the key is hello and all of the 3 blocks are encrypted with the same key, for example here the PY in the second block represented 60 and also the PY in the third block represented 60. So that's how a hacker, if he grabs hold of the encrypted ciphertext, can tell by the resemblance of 6 zeros that in the plain text as well there are multiple occurrences of some characters that he doesn't know, but still there are existence of some characters. So how this could be a problem in a real life? For example, you have made a password manager where you have used the ECB mode for encryption, and you are keeping your Facebook's and Twitter's password on that password manager. So assuming that your password manager is using ECB mode for encryption and the password you are using for the password manager's master password is hello. So the password of Facebook here you have used is QWERTY1234, and the password for Twitter is also QWERTY56778. So both of these passwords are encrypted using the password hello by the algorithm ECB or the mode ECB of AES, and these ciphertexts are generated. So for just example, say that the hacker grabs these ciphertexts and takes home the ciphertexts. Now what happens when he opens up those ciphertexts in his for example code editor? He can see from just the ciphertext that the first part of both the ciphertexts are exactly the same. So he can assume that whatever the plain text was, both the plain texts are also same, like as in here in the ciphertexts. So if he manages to hack or crack the first password, that is QWERTY1234, he can just tell by looking at the second ciphertext that the first part is also QWERTY. It will just be a matter of time to figure out that the password for Twitter is, the last part of the password of Twitter is 5678. He can just know by cracking the first password that the second password also starts with QWERTY. So that's how ECB is going to be a problem, that if there is a multiple similar resemblance in the plain text, there will be a multiple similar resemblance in the encrypted ciphertexts as well. Okay, so let's talk about Cipher blockchain mode and how it's better than ECB, and how this problem wouldn't be existing if we had used CBC instead of ECB, even if the passwords were the same. So how CBC works, let's talk. So for the first process is exactly same as ECB, that is when a message is supplied to AES for encryption, it breaks down the message into certain blocks of fixed length size of 16 bytes and is encrypted with the same key like ECB, but with one exception. Each block is chained to each other in a way, and I'm going to explain how. So what happens, the most important thing in CBC is that the first block has to have an initialization vector. So the initialization vector is basically a random sequence of characters that is added to the first block of the message to produce a more unpredictable form of ciphertext. But now the things get interesting. The ciphertext from the first block is XORed with the plain text version of the second block, and then the same key is used to encrypt the second block, and that produce an even better unpredictable ciphertext. That ciphertext is XORed on the third block's plain text and then encrypted with the same key to produce an even further unpredictable ciphertext. So thus, even if there are multiple occurrences of PY or the same plain text within the same blocks, like PY here and PY here, the values will be completely different. It's very unlikely that they will ever match. So that's how CBC is better, by randomizing the data on the start of each blocks. So maybe the current block is 5. So if the number of working block is the 5th block, for example, then the plain text of the 5th block is XORed with the ciphertext version of the 4th block, and then the 5th block is encrypted with the key, thus randomizing the data and thus linking all of the chains in a way that even if this case arises where the passwords are similar, the ciphertext versions will never be the same. So that's how CBC works. Now let's go to the Python shell and actually code these things. Okay, so before diving directly into encryption, I'm going to explain something called padding. So when I'm actually going to do padding within the encryption module, you are going to be confused, because I was confused as well, because nobody explained it how it worked from the roots. So that's why I'm going to explain padding before I dive into encryption. And as you know right now from the second or third slide, I guess, that padding is used when the number of characters in a message is not directly divisible by 16, right? So AES needs each block to be 16, and it can only work if each block contains 16 characters. So what if the number of characters in a message is 12? Then padding, what padding does is it fills out the rest of the remaining places with parentheses, right? So if the message, for example, is I love Python, and the length of the message, let's just check, message is 13. So what it would do is it will automatically do something like message equals I love Python, and then add 3 parentheses, thus making it, okay, so sorry, length of message is 16. Now AES can work because it works on a fixed length block size of 16 bytes. So it's not possible for a person or a programmer to manually add every time these parentheses by calculating what is the number of characters in a text or a message. So we have to automate that process, and the process of automating is basically block size minus length of message modulo block size times padding element, right? So that's how it's going to be done, and let me just show you in a more practical approach. So let's just do this again, where I intentionally keep it the length of the message being 13. So the block size in AES we know is 16 bytes. So let's just type in result equals message, which is I love Python, plus 16 minus length of message modded with 16, which is again the block size, times padding element, which is going to be the parentheses, right? So if I hit enter and print out result, it gives us I love Python and 3 parentheses. So it's going to be automated, and if I just check if the result is of 16 byte length, we can just check it by length of result. It's 16. So let's just check if it works with an even smaller message. So just maybe I love or ILOV, no problem, and do the same thing, and let's check what it does. So length of message is 5, so 16 minus 5, it should be it should give us 11 parentheses, I guess. So if I do this again and print out result, it gives us this much parentheses. So that's how padding works, and if the original message is greater than 16, this algorithm will automatically assume that the total number is being 32. So for example, I love Python and 3 parentheses, and if I add one more character to it, it becomes 17. So now this algorithm will assume that the total number is 32. So okay, let's just do that but in a practical example. So message equals to I love Python 3 parentheses and add another character by making it 7, by making it length of 17 characters. So maybe just add 0. Okay, and print out the length of message, that is 17. So what happens if I do this? Print result, sorry, see, after I love Python 3 parentheses and 0, it gives us this much parentheses. So if I just print out the length of result, it's going to give us 32. So it's the main job of this padding function is to make sure that the total number is directly divisible by 16, so that AES can make even blocks of 16 byte sizes. So that's how padding is done. Now I'm going to dive directly into encryption and directly do padding there. So I will not explain padding that time. I guess you understood what padding is. So let's go on to the next example of how to actually implement this in encryption. Okay, now let's directly jump into the encryption and decryption itself. So we are going to use the module Pycrypto, but the problem with Pycrypto is it's not maintained anymore. So that's why we are going to use Pycryptodome, which is exactly same as Pycrypto, but a more efficient and more stable version, which is maintained and works well on the latest versions of Python. So what you have to do is to go to command line or your shell, depending if you are on Windows or Linux, and type this command, which is pip install Pycryptodome. Anyways, I have already got it installed, so I'm not going to do that anymore, and I'm going to directly jump on the encryption part. So we are going to import two things. One is AES and another is the SHA-256 hashing module. And I am not going to do CBC mode here because CBC just takes one more variable. The coding part for CBC is simple, it's not hard. The understanding the theory part is just confusing, that's all. The initialization vector, you can just take IV and do a random function. So you have to import random first, of course. You can import random and keep the random value in the IV and pass in that IV to the AES object, thus making it a CBC mode operation. But for the simplicity of this video, I am just going to use electronic code block. So anyways, so first of all, let's import AES from crypto.cipher import AES, and from crypto.hash import SHA-256. So now let's act like it's a real life example, and I would prompt the user for a password. So the password would be input enter password. So the password is hello, as you remember. So if I just print out password, okay, what's happening? It somehow didn't take. Okay, let's copy and paste this again, and okay, just let me do this again. Password equals to input enter password, and the password is hello, print password. Okay, now it's done. So as you can see, I have told you on the AES key section that AES only accepts the key in 16, 24 or 32 byte long characters. Now hello is none of them, so we are going to use SHA-256 to stretch the key or to hash the key into a 32 byte value. So how can we do that? Just let's make a hash object. So hash object equals SHA-256.new, and we are going to pass the password, but there would be an error, and the error would be string cannot be passed. So in the world of cryptography, what you need is everything you need to do is in bytes. So I have to do the same thing here, just encode the password into bytes. So we can do that by just typing .encode UTF-8. Now the hashed key, I will be just typing H key equals hash object dot digest. By doing digest, I am actually spitting out the 32 byte long characters. So if I just print out H key, you will notice that H key, I guess it's 32. So if I just do H key, see, it's a 32 byte long character. So, and also it's in bytes. Anyways, now as the key has been generated, now let's go and directly move on to encryption. So def encrypt is going to be the name of the function, and we are going to send in some information. Let's just say info. Just copy the information into another variable. The block size, remember, is going to be 16. The padding unit is going to be this element, and we are going to use a lambda function for the padding, and I am not going to explain padding here because I already did that in the previous lecture. So padding is equals to lambda, just take a variable s, and s plus block size minus length of s modded to block size times pad. Now let's make a AES object. Cipher equals to, it's exactly like that, AES dot new. The key is H key, we have already done that, H key, and the mode of AES is going to be ECB. Right, now cipher, and the results will be stored in the variable called result. It's simple as that. Results equals cipher dot encrypt. We are going to use the encrypt function from this cipher object. So encrypt, I am now calling the padding function, because whatever I am doing here is whatever is passed into this argument is copied into the message, and I am going to send the message to the padding function, which will send us the complete padded out version of the message that we can use for encryption. So padding, and the message will be message, of course, and again encode UTF-8, because as you can see, when I was explaining the padding function in the previous lecture, it was in string, so it won't be working, so I have to encode it into bytes. So again UTF-8, thus completing the encryption function, and return the result. Let's see if it throws any error. It didn't throw any error, so let's just try to encrypt something. So again the message is going to be I love Python, and I'm going to call in the encrypt function. So a ciphertext, maybe taking the variable ciphertext equals to encrypt, and I'm going to send in message as the information. So if I print out ciphertext, let's see what it gives us. See, this is the encrypted version of I love Python. Now let's make the decrypt function. Now the decryption function starts as same as the first one, the encrypt function. So decrypt. Again, I do not need to actually say this time what is the block size and all, because it already knows it by now. So again info, I am going to copy the info into a message equals info, and then what I'm going to do is, again I'm going to say pad equals, because I have to unpad. Remember, when we pad some data, we have to also unpad the data out. So padding unit is going to be this one. So again decipher, let's make another AES object equals AES dot new, the key being, and the key has been passed, and again the AES dot mode is going to be ECB. So decipher, again we are going to call, like we called an encrypt function, this time we are going to call a decrypt function. So decrypt, and we are going to take that in a result, of course, result, okay, not result, maybe for example plain text equals decipher dot decrypt the message, which is this. So now what we have to do is, the message will come out not in strings but in Unicode. So let's decode to Unicode that also, and let's decode that to Unicode as well. Dot decode UTF-8, that's done. And now let's unpad. So let's just do pad index equals pt.find pad. So the result is going to be pt display everything until pad index comes in. So that is going to be the code. I guess I have done it right, and return the result. So we already have the ciphertext, so let's again print out the ciphertext to see if it's still there. And now let's maybe do plain text equals decrypt, and we are going to pass the ciphertext. So no errors are thrown. Let me check what happens. Print plain text. Oh, wow, so it's done. So that's how decryption is done. The decryption part is comparatively easy. What I did here is simple Python string operations. I'm not going to explain this, but that's how encryption and decryption is done in Python. So I guess I have made a good job in explaining what AES is, how encryption works, what is block ciphers, how block ciphers work, how CBC and ECB mode works, and I have shown you a complete definition or a complete explanation from 0 to 100 included padding, including when how to hash a normal text, how to take a password from a user, hash it out and use it as a key for encryption and decryption. So I guess this video is enough for you to start your own project or for you to learn further complex things, but this is the simple one, this is the start. So I guess this would help you. Until next time, until I come up with a new video, thank you for watching. If you like this kind of stuff, do subscribe and like this video, and feel free to point out if any mistakes I have made. So subscribe, like, comment, share and spread the knowledge. Until then, goodbye.